Welcome. We are in Unit 11, Exponential Functions, and this video will cover Day 2, Exponential Functions Evaluate and Graph. This is the first half of Section 6.3 from the book, and we will look at Objectives 1 and 2. Here are some examples of exponential functions. F of x equals 2 to the x, or f of x equals 10 to the x, f of x equals 1.04 to the x. This number on the bottom, that's called the base, 2, 10, 1.04. I'm also allowed to have my base be a number less than 1. 2, 10, 1.04, those are all greater than 1. I can have 1/2 as my base, or 0.07 as the base. And I can multiply that base to the exponent by a constant out in front, like the 3400. So 3400 times 1.05 to the x, that's an exponential function. What I'm not allowed is to have the base be a negative number. What's the problem there? So in order for my function to be defined, and I want it to be defined for as many x as I can, if my base is negative, what would happen if I tried to put in, say, 1/2 into the function? F of 1/2 would be negative 2 raised to the 1/2, but 1/2 is the same thing as square root, so this becomes the square root of negative 2, and this is where I run into trouble, because the square root of a negative number is not a real number. So for us, we say that's undefined. The problem with f of x equals 1 to the x is mostly just that it's very boring. I suppose I could have 1 as a base, but then this function is just constantly 1. Not very interesting. In general, here's what we say, that an exponential function is a function of the form f of x equals c times a to the x, where a is this base, a is greater than 0, a is not 1, and c is not 0. Here's an example, this c times a to the x, where I have c as 3,400. And this c not equal to 0, again, that's just almost to keep the function from being boring, because if c was 0, then my function would just be constantly 0 everywhere. Also, we allow some variations in what I call an exponential function. I can have 2 to the x plus 5. This is basically shifting the graph up 5 units. Or maybe let's make my exponent x minus 1. Or even have a negative exponent. In all cases, though, the exponent has the variable. The argument of my function lives in the exponent. So that's what makes an exponential function. Let's talk about this phrase, exponential growth. You hear this out in popular culture every once in a while. Something grows with exponential growth. What does that really mean? Here's an example. Say that I have a function f, and the value of this function f at 0 is 5. So in other words, f of 0 equals 5. This is what I see in the graph. F of 0 equals 5. And then the value of f doubles with every unit increase in x. This is the real key to the idea of exponential growth. There's some multiple, in this case doubling, that as x increases unit by unit by unit, the function values get multiplied by this thing again and again and again. That's exponential growth. Let's see if we can figure out the form of this function. Well, f of 0 equals 5. I'll start with that. F of 1. So f of 1 is twice f of 0. That comes from this second statement. The value of f doubles with every unit increase in x. So f of 1 is twice f of 0. Okay, well, I'll go back to my what I know f of 0 is. So that's 2 times 5. And I'll be a little bit clever here. You'll see why in a second. I'm going to write that as 5 times 2 to the 1. Now let's continue on. F of 2 is going to be twice as big as f of 1. So in other words, that's 2 times 5 times 2 to the 1. And now if I multiply and combine the 2's, I get 5 times 2 squared. Let's do this again. F of 3 is twice f of 2. And so I can write this 2 times, what was my f of 2? Oh, that was 5 times 2 squared. Multiply my 2's together. I have 3 of those, so that's really the same thing as 5 times 2 cubed. And we'll do one more. F of 4 is 2 times f of 3. So that, in other words, is 2 times 5 times 2 cubed. Multiply my 2's together, and I end up with 5 times 2 to the 4th. Do you see the pattern? I bet you do. F of 4 is 5 times 2 to the 4th, and in general, f of x looks like it's going to be 5 times 2 to the x. And this has the form of the exponential functions that I expect. It's c times a to the x. Now, what determined that c? That was my initial value. That was where the function was 0. Because if you imagine plugging in 0 into this function, all that's left is the constant out in front. And how about that a? See how that a is 2? It doubles each time. So if I had a function that was tripling each time, then that a would be a 3. If f of x equals c a to the x, then that c is called the initial value, and the a is called the growth factor of the exponential function. Let's talk about the graphs of exponential functions. The graphs of exponential functions all kind of have a similar sort of look. They have a long tail that approaches 0. It kind of squeezes down against the x-axis. And then as I move to the right, there's this growth. They grow faster and faster and faster. For example, I have here graphed y equals 7 to the x, which grows very fast, y equals 2 to the x, and y equals 1.5 to the x. You can see that as the base decreases, as the growth factor gets smaller, then the rate of growth of my exponential function decreases. There are two things that I want to point out about all of these graphs. First of all, they all go through the point 0, 1. Because look what happens if I plug in 0 into any of these functions. 7 to the 0 equals 1. 2 to the 0 equals 1. 1.5 to the 0 equals 1. Any number, if I raise it to the 0 power, is going to be 1. So that's why we often see these exponential functions passing through that point 0, 1. The second thing is to look, how can I see that growth factor in the graph itself? I can see the growth factor in the graph by looking at the x value of 1 and seeing the y value of that function at 1. So for example, 7 to the 1 equals 7. So I expect that this graph crosses right at 1, 7. So 7 to the x crosses at 1, 7. And 2 to the 1, of course, equals 2, and 1.5 to the 1 equals 1.5. And so I see that the 2 to the x graph has the point 1, 2, and the 1.5 to the x graph crosses through 1, 1.5. Here are some other interesting exponential functions. What happens if the base is less than 1, but still positive, but less than 1? We end up with something called exponential decay. And this is interesting. This happens a lot in real life, exponential decay. Things get smaller and smaller, approaching some limiting value. Here's y equals 1/2 to the x. And look how, as x marches on from left to right, for every unit increase in x, the value is halved. It goes from a value of 4 down to a value of 2. It gets halved. And then from 2, it gets halved down to 1. And then halved to 1/2, 1/4, 1/8, and so on, becoming 1/2 of what it was each time. The function 1/5 to the x is even more extreme. For every unit change in x, the y value is 1/5 of what it was before. How would I graph a function if I didn't know what the graph looked like from the beginning? Well, it is a matter of just plugging in some values. Here are some values for 2 to the x. Maybe starting down below, 2 to the 0 is 1, 2 to the 1 is 2, 2 squared is 4, 2 cubed is 8, and skip a little bit, 2 to the 10 is 1024, 1024. Exponential functions grow very quickly, and that's what this shows. But if I head in the reverse direction, look at this, 2 to the negative 1, that's 1/2. 2 to the negative 2, is 1/4, right? Because that's 1 over 2 squared. 2 to the negative 3, that's 1 over 2 cubed, is 1/8. And so these numbers, as I go up, they get smaller and smaller and smaller and smaller. That's like moving left on the x-axis. So, in fact, we end up with the graph that looks like this. Moving to the right, the value doubles each time. So the y value is 1, and then 2, and then 4. And if I move to the left, the function values halve each time, 1/2, and then 1/4, and then 1/8. A really nice way to graph exponential functions is by using transformations. So let's say that at least I know what 2 to the x looks like. Now I can graph some other things like 2 to the x plus 3, or 2 to the x minus 1, or 2 to the negative x. Let's graph these things. So how about we'll start off with g. 2 to the x plus 3. Well, do you remember what adding a constant does to the graph of a function? It just changes its y value. So by adding 3 to the function, I'm really adding 3 to the y value. So at 0, I initially had 1. If I add 3 to that, I'm going to get 4. When x was 1, I initially had 2. Add 3 to that, I'll get 5. When x was 2, I initially had 4. Add 3 to that, I get 7. Okay, that looks good. What about to the left? Well, maybe we can think about the whole tail. The whole tail of this function squeezes against the x-axis. So let's just lift that whole x-axis up 3 units. There we go. I'll line at 3. And so my function sort of approaches that line on the left, and then it increases going up. So that's how we might graph 2 to the x plus 3. How about the next one? H of x, 2 to the x minus 1. How is the graph transformed here? It is a shift, and since I'm modifying the x, it's a shift either left or right. Which way is it? This can be a little confusing sometimes. Well, there's nothing wrong with plotting a few points. Let's just try. How about, what if I plug in x is 0? If I put in x is 0, then the answer is 2 to the negative 1, which is 1/2. All right, plot the 1/2 there. What about if x is 1? If x is 1, then this becomes 2 to the 0, which is 1. Okay, I'll do one more. And if x is 2, then this becomes 2 raised to the 1, which is just 2. All right, 2 there. And so it looks like, actually, this graph is being shifted to the right 1 unit. And so maybe I would expect for my 3 that the answer is 4. So if I plug in a 3, this becomes 2 squared, which is 4. Yeah. And so it looks like the original graph just shifted to the right 1 unit. How about the next one? Graph p of x equals 2 to the negative x. Well, what kind of a transformation does this do? If I negate the x, it turns out that this reflects the graph over the y-axis. And so let's see how that works, if that's really true. Well, if I plug in 0, 2 to the negative 0 is still 1. If I plug in 1, this becomes a 1/2. If I plug in 2, 2 to the negative 2, that's 1/4. Okay, so yeah, it looks like it is descending here. It's decreasing. I have decay on the right. And what if I plug in negative numbers? So if I plug in a negative 1, 2 raised to the negative 1, that's just 2. And if I plug in a 2, all right, 2 to the negative 2 is 2 squared, and that's 4. All right. And so there we go. Yeah, it really looks like this graph is just the reflection of the original one over the y-axis. We've seen this graph before, haven't we? Doesn't this look a lot like 1/2 to the x? Could it be that these are really the same? And yeah, because look at this, 2 to the negative x. We know from our laws of exponents, that's the same thing as 1 over 2 to the x. And that's the same thing as 1/2 all raised to the x. So this exponential function, 1/2 raised to the x, can also be thought of as the function 2 to the negative x. All right, this is a good place to stop our introduction to 6.3 exponential functions.